Okay, so we're going to look at lines in R2 in this video, and we're going to look at how to create the vector and parametric equations of lines. So we are familiar with the equation of a line in the form y equals mx plus b, where m is the slope of the line and b is the y-intercept. So what we're going to do is think of it this way. We're going to create another way of representing lines in two space. So this way is perfectly fine and it has plenty of uses. But now we're going to kind of look at what we know about vectors. So we're going to learn how to take that and make it look like this. So this isn't going to make a lot of sense until we actually kind of see it. And once we kind of see it and relate it to something we've already been working with, you should be able to make that connection. So let's just look at this line here. So I got this line, I've highlighted 2 points on the line. So I've got the point 2, 2 and the point A4. Now again, we can use any 2 points on the lines, but I want you to look here, right? So let's go to the origin and let's go like this. So let's make this a vector, right? Let's make it hit that point 2, 2. Now it can hit any point on the line. I'm just gonna pick 2, 2 for now. So I'm gonna call that vector R naught when I got that little sub-zero. So vector R naught is going to be any point on the line. And it's also a vector because it comes from the origin, and that's position vector. We saw that before. So point on the line. Okay, now watch the red here. So remember, let's take that walk. I'm starting here, and I'm going to go here to 2, 2. And then I'm going to continue here from 2, 2 to another point on the line. Could be any point. So in this case, I'm just picking A4. So I've got a vector though. I've got a vector between 2, 2 and A4. That vector right there, we've seen in a prior video, is going to be the change in x and the change in y. So I'm just going to do that work up here. I started at 2, 2, and I went to A4. So change in x is going to be 6, change in y is going to be 2. Now remember in that prior video, we saw that right there gives you a vector that's parallel to that vector in question when you do the change in x and change in y. So 6, 2, if I were to graph that, 1, 2, 3, 4, 5, 6, and then up here to 2, it's going to change the color there, highlight a little bit. That's that vector right there. So that vector is the one representing the vector from 2, 2 to 8, 4. That vector right there we're going to call the direction vector, and that's going to end up being parallel to that vector, and because that vector is from that line, it's parallel to that line. Now, remember the triangle law of addition. Actually, I think the highlighter will be better here. So remember that path, like I start here, I go here, and then I go here, right? So then, I could also say, well, I could just take the shortcut being from here to here. Here's your triangle. So that part right there that I just highlighted, the shortcut, that's what we refer to as vector R. So now this is going to make a lot more sense because I'm saying that R is going to be equal to vector R naught, which again is any point on the line, plus the parameter t, I'm going to explain that in a minute, multiplied by the direction vector. So actually I've got enough right now to put this line right here, the line that contained 2, 2, and 8, 4, into vector form. So I could pick any point on the line, so I pick 2, 2, so I'm going to put that there for R naught, plus t multiplied by the direction vector, which we figured out, remember that was 6, 2, so I'm going to say direction vector m. Now you notice here, t can be any real number. Well, t can be any real number because if you had this, so suppose you had 2, 2 plus t, and then you had something like this. You had 18, 6. These two are the same. Now you might say, well, wait a minute. One is 6, 2, and one is 18, 6. Well, that's where t comes in, right? T comes in because if you look at 6, 2 and 18, 6, out of 18, 6, I could factor out a 3 there. And then notice I'm just right back to 6, 2. So that was that concept of collinear vectors we talked about. So in this case here, like t is actually 3. So the presence of that t just helps remind us that there is like infinite number of vectors we could use for direction vectors. Because basically you're going to have all these vectors that are parallel to that line. So you can't say one vector is the direction vector. You have to make an account for there also being all those other vectors that are parallel, and that's where that parameter t comes in. So but when you're asked to create the vector equation of a line, what you need is you need a point on the line, and it can be any point on the line, and then you're going to need that direction vector. So that direction vector is going to be the vector you get by doing the change in x and the change in y from 2 points on the line. And again, they can be any 2 points. So this right here, I'm just going to rewrite that. That is the vector equation. And when they want the parametric equation, think of it this way. Well, vector r has x and y. So then what you're doing for parametric, you're kind of splitting it up. You're saying x equals, and you take the x component 2, plus, you got to expand by that t, so plus 6t. And then y, so you take all the y components, it's going to be 2, plus, and you expand by that t there, plus 2t. So that right there is a parametric version of the line. And then remember, you've also got y equals mx plus b. So all three of these, vector, parametric, and slope-intercept form, are all different ways of representing the same line. So this is what it looks like in 2-space. So again, when you're working on these questions, you have to get used to the fact that there could be many different answers, right? Because of that whole thing about the parameter t and the direction vector, and also the fact that you could pick any point on the line to be your or not point. Okay.